Welcome back to another exciting episode of Dave Does Math from Home. We got a good one for you today. Today we're talking about section 8.4. This is trig substitution, which, based on the name, probably sounds a lot like what we were just doing in the last section. The last section we had trig integrals with like a bunch of sines and cosines to different exponents, and we were learning how we could substitute some of those using the Pythagorean identity into other versions so that we could eventually turn it into something we could do with integration by substitution. So there was a lot of trig happening and a lot of substitution, but that is completely different from what we're doing here. The integrals we're going to look at here don't initially involve any trig in them at all. They're just x's, or they're just integrals with weird x's in them in strange places. But we're going to substitute some trig into them to simplify them, and hopefully they clean up really nice, and then we can unsubstitute later once we've done the integral with some trig. So it's a completely different section. We're doing completely different stuff. It just sort of sounds similar in the name. So let's just start with some problems that we're going to do in this section. Let's start with a marker that works. That's probably a better plan. Okay, it's a little shaky. Here we have an integral symbol. I want to integrate 1 over the square root of 1 minus x squared dx. This is going to be a bit of a problem for us to integrate. We have a 1 minus x squared. That's the thing that's happening. That's like its own little mini function. That is in a square root that is in a denominator. That is two things that fully qualify as another function. So when we look at this, what we're seeing is a function inside of a negative 1/2 exponent. So very clearly composite functions going on here. If we try to do integration by substitution, it's not really going to work. We could rewrite this as 1 minus x squared to the negative 1/2 dx. We could do that. We could do some inside is 1 minus x squared, outside is blob to the negative 1/2, other is dx. This is a great start. If we try to finish this, we would set w equal to 1 minus x squared. dw would be negative 2x dx. And these don't match, and we can't make them match. The two we can account for. That's very easy to handle. The x is what's making this a big problem. If there was an x here instead of a 1, we could do this problem with substitution very simply. Because there's no x here, we need to find a different way to do this problem. But there's some good news. The good news, much like in the last section, is the Pythagorean identity. We know that 1 minus sine squared is just cosine squared. And we know that 1 minus cosine squared is just sine squared. So imagine if this 1 minus x squared business, imagine if it turned into a 1 minus sine squared. We could swap that out for a cosine squared, and then we would take the square root of cosine squared, and we would just have the cosine. And that's going to make this much, much easier. So let's try that. We're going to set up a substitution. I'm going to say x equals the sine of theta. If I'm going to do this, I also need to swap out dx for something. Dx is going to be the cosine of theta, d theta. And I can start swapping stuff around. I can say that this integral is the integral of 1 over the square root of 1 minus sine squared x, or sine squared theta, times cosine theta d theta. This is my dx. And I can simplify this business down here. We already said, according to the Pythagorean identity, that this is going to be the square root of cosine squared times cosine d theta. And the square root of cosine squared is just cosine. So this is 1 over cosine theta times cosine theta d theta. It got even better than we were expecting. Because now, 1 over cosine theta times cosine theta cancels. This is the integral of d theta. Or if this looks empty to you and you don't like it, put a 1 in there. It's the integral of 1 d theta. This is the easiest integral in the world. That's just theta plus c. Don't forget your plus c. But we're not done yet. The problem started with x's. We need to give our answer with x's. We can't just say it's theta without talking about the relationship between theta and x. This is the relationship between theta and x. So, if x equals the sine of theta, we need to know that theta equals the arcsine of x. This is what happens if we try to take the, if we solve this equation for theta. You do it by taking the arcsine of both sides. And the arcsine of the sine nominally cancels, mostly, usually, it's fine. So we just have theta equals arcsine x. So this integral is theta plus c, that's arcsine x plus c. Which is not very intuitive. You'd like to think that when you start with this weird, like, 1 over the square root of 1 minus x squared, like, arcsine's probably not the first thing that came to your mind when you thought of this. But if you dig up your old Calculus 1 notes, somewhere in that, probably late in chapter 3, 3.8, 3.9 maybe, somewhere in there. Somewhere in your old calculus textbook you will find notes from when we did the derivative of arcsine, and the derivative of arcsine is 1 over the square root of 1 minus x squared. So it makes sense that the integral of 1 over the square root of 1 minus x squared is the arcsine. That's what we're doing here with this. Some of these questions are going to get a little more exciting. Some of them are going to get a little weirder. We are capable of handling more excitement and more weirdness than this. So I'm going to start showing you what some of that looks like. First bit of excitement we're going to handle is what to do if there are other numbers involved. So I'm going to call this a 16 minus x squared. Let's make this a weird one too. Let's make this a 19. There you go. And we need a dx, of course. Okay, so looks kind of like the last one, has the same sort of general format. There's a radical in the denominator with an x squared being subtracted. That's kind of all we need to start the trig substitution process. So we're going to do trig substitution again. Here's what's going to be different about this one. If I set x equal to the sine of theta, then this on the inside will be 16 minus the sine of theta squared. 16 minus sine squared is not the Pythagorean identity. The Pythagorean identity is 1 minus the sine squared. So we need to make a different substitution so that we still end up with a 1 minus sine squared. If there's a 16 here, that means we need to get a 16 in this piece so that we can factor the 16 out of both pieces and then be left with 1 minus the sine squared. So if I want a 16 in this piece, I'm going to have to set x equal to 4 sine theta. And then dx will be 4 cosine theta d theta. And let's see what happens with the substitution now. I'm going to take the 19 outside. 19 was never really going to affect this at all. It was just going to get extracted instantly, which is fine. I'm going to have a 1 over the square root of 16 minus 4 sine squared will be 16 sine squared times 4 cosine theta d theta. So, now that I have 16s in both of these places, this 16 from the original, this 16 from 4 squared, I can factor that 16 out. So this is 1 over the square root of 16 times 1 minus sine squared times cosine, or times 4 cosine theta d theta. So, I got the 1 minus sine squared that I was looking for. Now that I have this, I can swap it for a cosine squared. The 16 is going to hang out for now. 19 can also hang out. This is 1 over the square root of 16 cosine squared theta times 4 cosine theta d theta. Hopefully some of you can see where this is going. Square root of 16 cosine theta. Let me do the 19 first. 19. This is going to be 1 over the square root of 16 cosine theta squared is 4 cosine theta times 4 cosine theta d theta. This is the thing I really like about putting numbers here. It feels like you're going to end up getting numbers involved here as well. But they also cancel. It's so good. 19 integrals of 1 d theta. The 4's cancel, the cosines cancel. We are once again back to the easiest integral in the world. This is 19 theta plus c. And of course, we gotta be careful. The integral was easy, but the unsubstitution step has an extra piece. We gotta deal with this 4 now. So, when we solve this thing, this is the relationship that we need to use to go from the thetas back to x's. When we solve this for theta, first we got to get rid of the 4. So the first step is x over 4 equals the sine of theta. Next step is theta is arcsine, not 4. Theta is the arcsine of x over 4. So we take the arcsine of both of these things, we get this. Final answer, 19 arcsines of x over 4 plus c. Some of you may be thinking, those simplification steps between the substitution and actually doing the integral were almost exactly like the substitution or the simplification steps we did in the last problem. You're correct. These substitution steps are pretty much exactly the same. I'm not going to ask you to do them every single time. There's a very clear pattern in solving integrals that look like this. Whatever number you have up here, that's going to be a coefficient. Whatever number you have in here, as long as x is by itself, whatever number you have in here will end up being the square root of that is the denominator inside the arcsine. So if you put like a 4 in here, then you'll have a 2 down the bottom. I'm saying this because your textbook includes a table of integrals, which has this thing as one of its integrals. The integral of a over the square root of b squared minus x squared dx. Anything that has this form will integrate into a as a coefficient times the arcsine of b over x. Sorry, x over b. Blah. Plus c. So if you're looking at the front cover of your textbook or the back cover of your textbook or somewhere in your textbook to see a table of integrals, this should be on there. You'll see something that looks like this. It'll tell you that the integral of this thing always has this form. And that's sort of the goal of what we're doing here. Going through these steps will, I mean, right now it probably seems fresh and novel, but the process really is exactly the same every single time. So I'm not going to make you go through it every single time. There is a formula. It comes from this process. You can use the formula if you want. There is still something I need to talk about in section 8.4, so I'll do that in the next part of this video. But this is the basics of it.